So, bond theory. We're now starting chapter 5, and bond theory is the theory about why bonds form. So remember, facts lead to laws, laws lead to theory. Facts are items, they are small pieces of information. Laws are patterns in those facts, and then theory is the explanation for the laws. Okay? We know that bonds form. We know a lot about when and how bonds form. Theory is for why bonds form. Why do atoms form bonds? So we're going beyond the thing I mentioned in the beginning of chapter 4, where it's just atoms approach one another and the nuclei are attracted to the electrons. This is valence bond theory, VBT. Atoms approach. The valence orbitals of those atoms overlap, and the electrons in those orbitals can now pair up. Okay, so the orbitals are able to share space, and the electrons can pair up in the shared space of those overlapping orbitals. So up top, we have two hydrogen atoms. They approach, their 1s orbitals overlap, and we get a hydrogen molecule with their 1s electrons paired up. Then in the middle, we have two fluorine atoms. They approach, their 2p orbitals overlap, and their 2p electrons, their unpaired electrons, can now overlap to give us a fluorine molecule. And then down here, we have hydrogen bonding with chlorine. The 1s orbital of hydrogen overlaps with the 3p orbital of chlorine. And the result is a hydrogen chloride molecule. The overlapping space allows the unpaired electrons to pair up. Electrons want to be paired. They need to exist in orbitals. Valence bond theory suggests that bonds form when orbitals overlap and thus allow the electrons to pair. So, bonds form when the orbitals overlap. Now, there's a weird thing. The orbitals have to have the same phase. So it's a little bit hard to see because of the colors, but the p orbitals have different colored lobes. This is light over here. This is dark over here. Light on the left, dark on the right. The other one is opposite. Dark on the left, light on the right. In the mathematics that underlies atomic orbitals, orbitals have signs. An s orbital is either entirely positive or entirely negative. That's why it's all one color. For the p orbital, one lobe will be positive, the other lobe will be negative. There's a bit of complexity as to what the positive and negative actually mean, but for the purposes of this, they have to have the same color, they have to have the same phase. So these need to both be positive in order to overlap. Okay? If one is positive and the other one is negative, then they can't overlap. They would cancel each other out, more or less. Each orbital has to donate an electron. That's how you get a covalent bond. And both atoms share the two electrons. Okay, so there's nothing too new in most of that. The next thing is that more overlap gives you a stronger bond. Okay? So the two hydrogen atoms, according to valence bond theory, don't have a wonderful bond because it's hard for those s orbitals to overlap. They're spherical. They have to get really close in order for you to get significant overlap. Okay? But the fluorine atoms, these p orbitals, are highly directional. Okay? They point out to either side. So it's really easy for them to overlap. Remember, p means peanut, s means sphere. Okay? It's really easy for the p orbitals to overlap because of the way they point out to either side. So the atoms don't have to get nearly as close. Notice that the center of the fluorine atoms are much further apart here than the hydrogen atoms are up here. So more overlap gives you a stronger bond. Okay? And the other thing is that because orbitals have directions, this gives you directionality to your bonds. Okay, so the bond is entirely in between these two fluorine atoms because that's where the orbitals overlap. Okay? Similarly, the two hydrogen atoms have the overlap here in between the two atoms, and thus that's where the bond is. Now, the problem with valence bond theory lies in geometry. Okay? So the three p orbitals, x, y, and z, is what they're called. They lie on the three axes, the X, Y, and Z axes. They literally are 90 degrees apart. Okay, so let me draw that really quick. Let's get the camera pointed properly. Okay, so here we have the three axes of the three dimensions. So X lying left and right, Y going in and out, Z going up and down. Thus, the px orbital lies along the x-axis. The pz orbital is going up and down, and py is going in and out. So that's great for allowing the orbitals to overlap. It's great for giving bonds some directionality. But how do you get 120 degree angles for trigonal planar or trigonal bipyramidal molecules? How do you get 109.5 degrees for a tetrahedral molecule? The way you do that is by summoning Yog-Sothoth, from beyond the planes of reality to drive the minds of men mad and bring an end to the world as we know it. Okay. That is to say, the answer is going to lie in hybrid orbitals. The only way we can really get the proper answers is by moving beyond the orbitals as we know them to something a little bit different. Okay, it's going to be hybrid orbital theory. So rather than starting a new video, I'm just going to proceed directly into lecture 25, hybrid orbitals. Okay, now in quantum mathematics, okay, say you have some question you need answered. If A and B are solutions to a problem, or if they're answers to the math problem, then so are their linear combinations. A plus B, A minus B, 3A plus 2B, 15A minus 21B. Okay? If these are all possible solutions, then those are the answers. So for example, when I say answers to a problem, I'm talking about y equals 2x plus 3. Okay, one answer would be, well, the set of solutions to that would be, the line y equals 2x plus 3, looking like that. Okay, x-axis, y-axis, y equals 2x plus 3. So one answer would be, like 0, 3. Another answer would be 5, 13, right? So those are, possible answers to this problem. Now, quantum math has much more complicated sorts of problems and thus gets more complicated sorts of solutions. But one of the neat things about quantum math is if A and B are each individually solutions to that problem, then so is A plus B, so is A minus B, or 3A plus 2B, 15A minus 21B. You can plug them in and you'll get the correct answers out. They're called linear combinations because, like 2x plus 3 is, nice and linear, a nice straight line. There's no squares or cubes and things like that. No square roots, just linear combinations. So for atoms, the question is, where do we find the electrons? Okay, the quantum math is what gives us atomic orbitals. Okay, so if S, what we've looked at before, what we learned about before, S orbitals, p orbitals, d orbitals, f orbitals, all the energy levels, those are possible solutions to the quantum math of where do we find electrons. Which means that we can get different orbitals where electrons can exist by making linear combinations of those atomic orbitals. Okay? So welcome to Friendship Dome. This here is a movie from Once Upon a Time, Welcome to Thunderdome, or actually Mad Max Beyond Thunderdome. With Thunderdome, 2 men enter, 1 man leaves, and Mel Gibson had to kill a guy. With Friendship Dome, 2 orbitals enter, 2 orbitals leave, and now they're friends. So what that means is that to get a linear combination of atomic orbitals, you bring 2 orbitals in, you mix them together, and you get 2 new orbitals out. Okay? So for example, here we have an s orbital, and here we have a p orbital. Remember earlier I was talking about in the valence bond theory how it matters that they're positive or negative. Well, here we have positive. The s is entirely positive. The p has a negative lobe and a positive lobe. So when you mix them together, you add them together, positive adds to positive, negative reduces positive, right? So this is the s orbital plus the p orbital. The positives add together and you get this really big lobe on one side, but the positive and negative, cancel out and you get this really tiny little lobe on the other side. But what happens when you do s minus p? Well, the signs flip, okay? Like 2 minus 3 is negative 1. 2 minus negative 3 is the same as 2 plus 3, right? So the negative, when you subtract the p orbital, the negative becomes positive, the positive becomes negative, and thus you get this orbital looking thing over here. Tiny lobe, big lobe, but they're on the other sides because the positive and negative added together in different ways. So we add these two together and we subtract these two, okay, 2 orbitals in, 2 orbitals out, we get these 2 new orbitals. And this is important because it gives us this lopsidedness. It gives us this really big lobe pointing out in one direction. And this gives us a really big lobe pointing out in the other direction. Meaning we can use these 2 orbitals to form 2 new bonds in a linear fashion, a linear geometry, right? One bond on one side, one bond on the other side. Okay? Remember that valence bond theory says that more overlap makes for a stronger bond. So if we have this hybrid orbital pointing out really far in one direction, that means we can get a lot better overlap in that direction, meaning we can get a better bond. Okay, and now a really great thing is that friendship is non-exclusive. If we put 3 orbitals in, we're going to get 3 orbitals out. Okay, so we mix s, p, and p, then we'll get 3 orbitals out, and we call them sp2. Okay, so this is an s orbital, this is a p orbital. These hybrids are known as sp hybrids because they're hybrid orbitals, and they're made of one s orbital and one p orbital. Okay, so let me bring up the camera. S plus or minus px gives you 2 orbitals. One, looking a little lopsided like that. One, looking really lopsided like that. And this is an sp hybrid, and this is an sp hybrid. Okay. Meanwhile, if we mix, an s plus px and py, okay, the result will be 3 orbitals. But now we have, s pointing out in all directions. We have x pointing only along the x-axis, and we have y pointing along the y-axis. So the px orbital meant that our orbitals could only point along the x-axis. But now that we're mixing x and y, our orbitals are free to be along the entire, the xy plane. Okay? So now they're going to be spread out in 2 dimensions. So we're going to get 3 orbitals. They're going to have the same general shape, that really lopsided thing. Only now they're going to be pointing in multiple directions. In fact, they're going to be pointing along, 120 degrees, giving us that nice trigonal planar arrangement. And each one of them is a hybrid orbital, so plus or minus, 3 orbitals in, 3 orbitals out, and they're not just orbitals, they're sp2 hybrids, because they contain a s orbital and 2 of the p orbitals. So each one is an sp2 hybrid. So that's how we keep track of what kind of orbitals are contained in the hybridization. So if we get 4 orbitals in, an s, a p, and a p, so px, py, pz, that gives us 4 orbitals coming out, and they're now sp3 hybridized, because they contain an s and all 3 p orbitals. And that gives us, 4 orbitals. That's a nice 3-dimensional geometry. It's the tetrahedral geometry. If we put 5 orbitals in, we're going to get 5 orbitals back out, and they are going to be d sp3 or sp3d. Okay, remember, there's only 3 p orbitals, so if we want to go beyond 4, we're going to have to start bringing in d orbitals. Okay, and 6 orbitals in, we're going to get 6 orbitals out, and they're sp3d2 or d2sp3. You can write it either way, sp3d2 or d2sp3. I've seen it both ways. It's perfectly normal, just however you feel like it. Oddly, nobody ever switches S and P, but they do put D on either side. Who knows? It's weird. Okay, the point is, whatever geometry you want to look at, you can get a hybridization for it. Okay? So, two orbitals gives us, two orbitals in gives us two orbitals out. They're sp hybridized, and it's a linear geometry. S3 orbitals, sp and p, gives us three orbitals. They are sp2 hybridized, and they give us that trigonal planar geometry. Four orbitals, sp-p-p, gives us sp3 hybridization and a tetrahedral geometry. sp3d is a trigonal bipyramidal geometry, and sp3d2 is an octahedral geometry. Okay. So how do we know what hybridization we have? You draw the Lewis structure. This is what gives you your hybrids. Okay. The coordination number, that is how many atoms or how many satellites you have, how many electron domains you have, is the coordination number. That gives you how many hybrid orbitals you need. So if your electron domain geometry is linear, that means that is to say, if you have two electron domains, you need sp hybridization. If you have three electron domains, you need sp2 hybridization. If you have tetrahedral geometry, electron domain geometry, not molecular geometry, but electron domain geometry, it's sp3 hybridization. For trigonal bipyramidal, sp3d, and for octahedral geometry, it's sp3d2. So, again, like I said, you need to be good at drawing your Lewis structures. If you can draw your Lewis structures, you can get your geometries, and you can get your hybridization. Okay. So, these hybrid orbitals form bonds according to the valence bond theory we got before. So valence bond theory and hybrid orbital theory go together like chocolate and peanut butter. Okay, this is the Reese's peanut butter cup of chemistry. Valence bond theory says that orbitals overlap, and this is what allows you to get a bond. Hybrid orbital theory says that you can combine atomic orbitals to get new hybrid orbitals, and these will get you the molecular geometry you need. So down here we have ethane, C2H6. So at the center of these yellow blobbies is a carbon atom, and these blue circles are your hydrogen atoms. Okay? Your carbon, okay, let me draw the Lewis structure of that really quick for you. So ethane is C2H6. You have carbon, carbon, and each one has its octet filled out with bonds to hydrogen atoms. So each one has, 4 electron domains. Each one is going to be sp3 hybridized. Meanwhile, the hydrogen doesn't need to hybridize. It just has the s orbital. In fact, it can't hybridize. It only has access to that s orbital. But that's fine. It can still form bonds. So the carbon atoms get those sp3 hybrids, giving it that tetrahedral geometry. Then all the atoms come together, and this hybrid orbital overlaps with this hydrogen to form a bond, and so on. And this hybrid orbital overlaps with this hybrid orbital, gets you your carbon-carbon bond. And that's what gets you your C2H6 molecule. Okay? Just a lot of orbitals overlapping. You have your hybrid orbitals on the carbon atoms and unhybridized orbitals on your hydrogen atoms. That's perfectly fine. Likewise, ammonia, NH3. The ammonia has 3 bonds, one to each of the hydrogens. It also has a lone pair. And thus, it has 4 electron domains. It needs an sp3 hybridization to get the tetrahedral electron domain geometry. So, valence bond theory and hybrid orbital theory come together to give us an explanation of why atoms form bonds. Okay, well, more how they form bonds. Okay, the electrons exist in atomic orbitals. These orbitals overlap to form bonds. Okay, so that's what we're seeing here, is the 1s orbital of hydrogen overlapping with this hybrid orbital of nitrogen. The unpaired electrons are now paired, they're shared, and they're more happy that way. in order to get the appropriate geometry, so that these electron domains are as far apart as they can be. That's where we combine our atomic orbitals. We get these linear combinations, and we get hybrid atomic orbitals out of it. In the case of nitrogen here, they're sp3 hybridized. Okay. So that is hybrid orbital theory. Okay. I know it's weird and it is confusing, but that's just the way it's got to be. The world of atoms and electrons and so on, that's just a really weird world. Things are different down there, and that's just the way it is. So, what do you have to know? Okay, first off, you have to know about valence bond theory. You have to know about orbital overlap, and better overlap making stronger bonds, and the orientation of the orbitals giving the direction of the bonds. And for hybrid orbitals, you have to know however many orbitals you put in is how many orbitals you get out, and that is what gives you the geometries that you're looking for. And so you need to be able to use your Lewis structure to get your electron domain geometry, and knowing your electron domain geometry, you know what hybridization you need. All right. And that is it for this evening's videos. I will be doing the rest of Chapter 5 tomorrow night. I will see you